Hochschule, and he's going to be speaking today about Rota's vision and the Lehmer conjecture.
Yeah, thank you very much, Larry and Ian, for inviting me. And I hope we will have a good 1 hour on some very new hot topic, which got some very high interest in the last 2-3 years. And some of the people involved in this are also listening today. So it would be interesting to see how to go further with this. Okay, so I have 1 hour. I try to be a little bit faster. Let's see. So I will talk about what has this to do with Rota, Lehmer, and then I will give some update on an extension of a Serre table on non-vanishing of Fourier coefficients of the Dedekind eta function. Then I will talk about the Dark polynomials, and I will explain them from an analytic and algebraic approach. And then we will go to some generalization. And at the end, I will talk about the Bessenrodt-Ono type inequality, the Chern-Fu-Tang conjecture, results of Brinkmann, Rowland, Tripp, and Kane, and some just recently appeared paper of Markus Neuhauser and myself. Okay, that's the program today. And maybe when the time runs out, I will skip some part, but definitely we'll talk about the last part. Okay, so we talk about the basic object is an infinite product, and we are interested in the coefficients. You can see this from a combinatorial viewpoint, but also to see this more or less as the Dedekind eta function to some power r. And this is very classical. Euler looked at the power of 1, and you know all these formula with the pentagonal numbers, then to the power of 3, and to the power of -1. Of course, everyone knows these are the partition numbers which appear, and Lehmer conjecture is about the power 24, about the non-vanishing of the coefficients. Actually, Rota said, and he believes that more or less a lot of combinatorial problems should or can be seen or transformed as where are the zeros of certain polynomials are lying. So to putting this in some, and then maybe even combine it with some combinatorial interpretation. What do I mean here about this? When we define below, you see this inductive definition, recursively definition of polynomials, where sigma k is the sum of divisors. Then we will see these Ramanujan numbers are actually the special values of these polynomials at the value -24. And you have to shift by n-1 because of the q of the discriminant function. And a typical picture of the distribution of the zeros looks like the picture above. So to zoom in on the abscissa, you have the real part of the zero, and the ordinate, you have the complex part. So red are the complex roots and blue are the real roots. And one can see already some pattern, especially when you look at, this is the polynomial of n is equal to 1000. Now let's look at a polynomial, let's say of 500. And they look somehow similar. At least you see some pattern. And but this is all not solved yet, but of course it gives some idea what to prove. For example, why is the largest root as in the absolute value always real, for example? This is still an open question. Okay, when we zoom in at the value -24, you see when we go to the polynomial 500, of course we know the tau value is non-zero, and you can see here the closest roots are complex numbers to -24, but this is not the general pattern. Sometimes it's, of course it would be nice to prove that it's always complex, but then of course we know it will never vanish, but that's not true in general, for example. So this pattern is not true. Okay, so what is known? For example, in the power, when you take, in the odd case, take odd powers. So when we take the, to the power, when we take the set of powers 1 and 3, it's well known that in this case, a lot of coefficients are vanishing. It's more or less like a quadratic form, as for example, the eta function can be written. It's called super-lacunary. And in the even case, Serre proved it's lacunary. That means, in some sense, when you count the coefficients which are 0 and you divide by n, then this quotient limit is non-zero. So, and there you have these exceptions 2, 4, 6, up to 26. And these are the so-called, in this case, for the SL2 set, the CM forms. So it was known also by Rippet that you have these lacunary vanishing, but Serre proved in 1985 that it's also the converse direction. Okay, then there's then also Serre recorded in his 85 paper that in the case to the power of 5, for these ends you have the vanishing, and for r is equal to 7 you have the vanishing as at 28,017, and at 15 power 15 at 53. Now we all know for small powers we have Hecke eigenforms of odd weight. And in some sense, when you normalize in the right way, you can see this as translate this as discriminants. And then we all know when D is the discriminant, that dm square is also vanishing because of the Hecke eigenvalue property. 2 years ago, we extended this table and checked because it was like, as you remember, it was 5, 7, and 15. And we had been wondering what's to the power of 9, 11, and so on. And we found out up to these powers, which you see on the right side, there are no other odd r's where the coefficients are vanishing numerically. So, but you can see in the case 5, and it looks like we've done more calculations that maybe there are infinitely many sources. That means fundamental discriminant, but that's not clear. Now in the even case, it's even more impressive. There's no case in literature, and we also did not find any other power different from the Serre numbers where any coefficient is vanishing. So it looks like that all even powers different from these numbers don't give us any coefficient which is vanishing. So this looks already as can be seen as a generalization, at least numerically, some evidence for the Lehmer conjecture. And maybe should look for a different proof, not just for the power of 24, maybe one should also look for a more general proof. And also, which is maybe interesting to say, people told me, maybe it's actually an eigenvalue conjecture. But when you take the discriminant function to the power of 2, that means eta to the power of 48, the so-called Maida conjecture about the Hecke polynomials and the Galois group is actually equivalent to the non-vanishing in the case of delta square. That means to the power of 48, which is definitely not a Hecke eigenform. Okay, so what we have done, that's somehow the basic, one of the basic ideas is we look not just to the power of r, we look at complex powers and normalize it by minus z. And it turns out that now these coefficients here, which had been before the an minus r, when here was a r and here was a r, are polynomials of degree n and really degree n. So that means when you fix the n, there are only n powers which which contribute to the vanishing. That means one idea to prove the Lehmer conjecture would be to find n roots which are different from -24. And these polynomials had been studied by Darche, François Carte, Italian guy, 100 years ago. So what I just said, and you can normalize this polynomial by n factorial divided by x, and then you get integer coefficients. And it's also easy to calculate because as you have seen on the first page, it's also possible to define them recursively. That's just because that you take the logarithm derivative of the identity and then you get this recursion formula. So the first polynomials have integer roots. For example, when you take the P3 minus 8 means you take the 8th power and the third coefficient, and that one is 0. And then you have the x is equal to 0, and actually it turns out you have also -1 to be 0. That also means when you take the P3, when you take the third coefficient for any other power, it's never 0 because of this polynomial finiteness property. So here you see the normalization given. So the AKs are all, actually they are even, and that's very important also, they're all positive. That means when we have real roots, which you have seen in the plot before, all real roots have to be negative because the coefficients are all positive of the polynomial. What we also observed, we cannot prove yet, but which is very interesting, there are always linear factors and then some irreducible polynomial. And the linear factors, of course, and the linear factors are also given by integers. Of course, but the point is, it looks like that the degree of these irreducible parts increases. Also because we have integer coefficients, all roots are algebraic integers. So for example, we know 1/2 or 3 divided by 2, and something like this can never be a root. Now when you look at this picture, we plotted the first 100 polynomials. So on the ordinate axis, you have n goes from 1 to 100. And on the x-axis, you have the real part. And you see the range of the zeros increases. And you have, it looks very nicely, very structured on the left side. And on the right side, you also have, which is red, complex roots, which somehow makes it actually good, because the more complex roots you have, the less real roots occur. That means the higher is the chance that the Lehmer conjecture is true. On the other side, the complex roots are also, of course, difficult to handle. Now, when you zoom in to the first 10 polynomials, you can see that in the first time a complex root appears is when n is equal to 10. This also was found or discovered by Marcus and myself. Now, what is open? It's open by all these plots one can and also calculations one can see it always, and this is done up to 1,500. That all roots seem to be simple. And what we found out, and this seems to be very, very interesting, all polynomials are Hurwitz. That means the real part of the complex roots are all negative. Now, when this would be true, one could make an interpretation of these polynomials at the characteristic polynomial of a stable dynamic system. But this is beyond, at the moment, what is possible to prove. But that would be really, really interesting to go deeper in this. Now, we started to look at what I just said, Hurwitz property. So what about roots on the imaginary axis? Is it possible to prove there are no roots, only x is equal to 0 there? So the question would be, when we plug in I, can P and I be 0? And we have been lucky, very lucky to meet Florian Lucca, who joined us in this project. And we had been able to prove 2 years ago that whenever you plug in root of unity and assume this root of unity is 0, the value is it's a root, then the root of unity has to be -1. That means that's the Euler formula when you take eta and you have these pentagonal numbers. So that's the only root of unity which gives you a root. And the proof went in the direction of, we looked at the recursion formula of the polynomials, we multiplied by the denominator, and then we looked at it mod p and used algebraic number theory to prove that. Now, it turned out that the recursion formula, which we have seen at the beginning, or the way of defining this polynomial, seems to be, sigma is a very complicated function. I mean, we all know you can formulate, for example, the Riemann hypothesis by this Robin inequality. So it's clear sigma, even when it looks quite simple with the sigma involved. So one idea would be to plug in this recursion formula upper and lower bounds. For example, Gn equal to n or Gn equal to n square, which puts the sigma n in the middle in the variation. And so this is now very important. So we look at this recursion formula, and it turns out that's the observation when we put sigma n, when we put this G here in this recursion formula to the divisor sum, then we get the dark K polynomial, the polynomial we started with in the beginning. So this very innocent polynomial at the beginning can be, this definition can be generalized by such a formula. And of course, you can ask, can you find a good G, or what kind of G you can plug in to get maybe polynomials which are known. And it turns out when you plug in the identity Gn equal to n, that means the lower bound, then these polynomials are actually a little bit modified, associated Laguerre polynomials. Now that's very interesting because the Laguerre polynomial actually have very nice properties. They are orthogonal, they have real roots, simple roots, and interlacing. Now, what is possible, and you have seen the range of the roots, we have been able to prove a growth condition for these dark K polynomials of this type. And of course, when you look at this in the recursion formula, it's obvious that these polynomials are different from 0 when you go, when kappa is, we proved when kappa is 10.82. So that means it's more or less linear in n-1. The root zone actually goes with n-1. This is very interesting because this, I will show you this later. There have been work of Kostant, Han, Nekrasov-Okounkov, also looking at this vanishing property, and they had using McDonald's formula and so on much. So their estimation goes with n square, and here with this recursion formula we found out it goes with n. Now we go one step further. Instead of putting here x divided by n, we say let's be more flexible. Let's put x divided by hn. So from the original recursion formula, x divided by n and sigma k, we now got to, let's say, the most general version at the moment. We say we take here an arithmetic function which is non-vanishing, and we take here another arithmetic function. Now, why is this useful? Actually, it turned out when we put Hn equal to 1, that means when we take the recursion formula x, we get the same zero-free zone, but not now with kappa times n minus 1. It's now just with kappa. So now the roots are concentrated in a finite interval. And actually, it turns out when we again take Gn equal to the identity, now these polynomials are the Chebyshev polynomials of the second kind. And as many people know, and it's the only case of orthogonal polynomials where the roots have explicit formula. So this is like the prototype, what we best can expect. Now, when we look now going back or forth to the plot now of such a polynomial, n is equal to 500. So again, so just changing the x divided by n to just x, we get from the infinite, that means from the zero zone, kappa n minus 1, we get now a zero zone kappa. And we plot it here now again for 500, the root distribution, and putting them next to each other, you can maybe see at least there are some pattern which makes it worse beyond this root distribution interval, also to say, okay, we have complex roots here, and maybe P and Q have something in common.
Does it look like, oh, could we just look at that plot for a second? I'm just, the red, they look like they lie on some curves. Like, do they look like conic sections or something? Like the left kind of looks like hyperbolas and the right looks a little bit like ellipses. Does it seem like some actually special curves or?
Yeah, I mean, there are some approaches in this direction in the orthogonal case, so-called Szegő curves, where, but actually we a little bit stuck at this point. We did not found, when I showed this to Don last year, he immediately went to his office and said, let's calculate something, and we tried, but it seems to be, I mean, they have to be, I mean, especially the right side. I mean, they look like you have an arrow and you have these loops. I mean, it's very symmetric. There has to be something. And that's actually the idea of the whole talk, to have this complicated thing, but maybe from a global viewpoint, you can see some, it's like the sigma function. When you look at, when you make the average, you also see some pattern. When you look individual, you have no chance. Mm-hmm. So that's the idea. And also, again, you also see that on the left side, on both pictures, you have real roots. I mean, it's obviously, and you have some staccato. I mean, there's some kind of, like in music, you have the distance between the roots gets smaller and smaller when you go from the left to right. And it should be possible to prove this. I mean, it should be not too far from the techniques we know. And of course, when you go to the right side, we always say there's the cloud, especially when you look at -24 on the left side. You also see the complexity, how difficult maybe the Lehmer conjecture is from an analytic viewpoint. I mean, the -24 is like, yeah, I will say something to that in in one of the slides. Okay, here we put now the 101st polynomials and plotted them again. The x-axis is the real part, and the ordinate, you have 1 to 100, and you have p on the left side and q on the right side. And again, when Gn is equal to n, you would have on the left side the Laguerre polynomials, and on the right side the Chebychev polynomials. So there has to be, and both are orthogonal. So there is some pattern. Now, what we've done here on the right side, on the left side, now you see below the interval went from 1 shrink to -10 to 0. So we looked at the argument of P by X times kappa times n minus 1. So we normalize them, which you always also do when you look at the root distribution of Laguerre polynomials. And you see somehow there are some you see that the complex roots are not completely arbitrary, especially these ones here. And yeah, now this is just to show you how many complex roots and how many real roots have. So you can expect when n goes to infinity, there's already some proportion of complex roots, but we believe that the real roots are dominating. At this moment, a short summary. When we put h in one case to the original case to equal to n, and then in another case we put in the second case we put it to identity 1, just to structure and simplify the notation. We put here p, and in this case you put q. Then we have this theorem saying these are different from 0, or we have this root zone, and you see here the pattern. And actually, when you look at this numerically, you can put here something like 9.78, which is reached, and we have some idea to get closer, but at least you see it's already very close. And you have to see that before there was an n square here by Kostant and Han and other people. So we went from square to linear, which of course numerically make a big difference when you want to check if there's an integer root. And again, for both polynomials, numerically we have the Hurwitz property. That means the roots go very close to the 0, but it seems to never reach only x is equal to 0 or z is equal to 0, the imaginary axis. So from that viewpoint, also it's worth to look at both these polynomials. Is there any question, again, another question so far? Okay, if this is not the case, but you always can ask. Okay, this is just a small thing. When you look at these recursion formulas, the P version, in the P version, the coefficients of this difference equations are dependent on n. In the Q version, they are not dependent on n. Now, these recursion formulas, which are not 4 or 5 terms, you know, for every n, the amount of terms are increasing for the channel pattern. They are studied in the Q case. I mean, not in our polynomials, but the Q case is studied or can be studied by the so-called Volterra type differential equations. When you have a k term recursion, there are theorems of Perron and Poincaré by saying when the limit of the quotients of the coefficients somehow are constant, then you can see it in the limit as a differential equation of constant coefficients, which is in the Q version. So one idea would be to study by Volterra the Q differential equation and hopefully transfer some results then to the P version. And so this would be the Volterra approach. And you would have this identity. So it's called the set transform, which you have on the left side denominator. But now the surprising fact is, I think when you, for example, look at, and this will I think immediately give you a sense what we are going in the next slides. When you put x0, let's say to 24, and Gn to sigma n, and z to the minus n to the q to the n. I mean, you will immediately realize this is 1 divided by the Eisenstein series of weight 2. So also even more general, you can see the left side for special G and special x0 as the reciprocal of the J function, reciprocal of Eisenstein series. And then you can use our theorem about no zero zone, which gives you a result when you write this as a power series. On the non-vanishing of the coefficients, actually get the sign change property of this coefficient. So this is also published. So when you want to go deeper in this, I recommend research journal of research of number theory published a paper on the coefficients of the 1 divided by the J function, and which reproves the result of 3 Japanese people. Very nice paper of, I just remember the middle one is Kaneko on the sign changes of the reciprocal of the J function. But when you look at our paper, this method can be used for also other cases, and actually proved also it also works for the Weber function or the cubic root of the J function. And there's a recent paper in the International Journal of Number Theory, which is related also to work of Brinkmann and Kane, and of course Ramanujan, Bernd, and all these people on the reciprocal of Eisenstein series. And there's a new paper in just 2 months ago, we put an archive where we went even deeper, where we used also analytic property like residues and what's happening on the border of the when we have where do we have a pole, a double pole? For example, when when you have Eisenstein series of weight 12, there are actually with the same height in the fundamental domain, you have actually 2 roots. I mean, in the E4, you have only 1. That means when you look at these residue limit theorems on the border, it makes a big difference if you have 1 pole, a double pole, or you have 2 poles. But you can see some poles dominate, so you can even still say something. So this is, I think, also quite interesting. And this was actually surprising when we went to the Q, that we saw we can also use this for studying such kind of reciprocals. And what I also mentioned several times, not mentioned several times, but we just look at the set transform, but it's also well known when you look at the Dedekind eta function. This is also always used in Borchards, by Borchards product. You can write it as an exponential version when you have here sigma, and it's the same when you put in G. So G is just a generalization of the powers of the eta function. But the point is, of course, this is not anymore I mean, you can formally write this again as an Euler product when you use just the Möbius inverse formula. When you write this as the sum of a function and d divided by n, and you write this, which is actually a sigma function, is the sum of the divisors. So you could go back to the Euler product. And but so this is, I think, quite important point that you see. And of course, when H is more general, then we are here somehow between. I mean, when H is equal to n, then we get this formula of the recursion. And when H is equal to 1, then we get this formula. But there's not a clear formula when Hn is maybe n square or whatever, then it's not so clear. And one idea, of course, is it possible to transform this formula to this formula by using the H? Okay, and here is, as I just said, this is the recursion formula. Now this is just, I do this part quite shortly. which is also an application. You know, this is this famous table which appeared already in Ramanujan's 1916 paper, which, you know, all these things came from: congruences, multiplicative properties, conjecture, growth condition, and but also you can see when you look at the coefficients, there's a sign change, and the first non-sign change appears from 6 to 7. And actually, when you look at these polynomials, especially the table up to 10, this is the first case when somehow two roots appear left to minus 24. I mean, or in other words, when an even number appears. I mean, normally when you are outside the root zone, the polynomials behave like x to the power of n. That means when you have any value out of the root zone, it's just and you have to make the shift because we put away the q. So that means it's that the odd numbers have an even power. That's the x to the n, and then this is the first case when you look at it. So actually the table proves, or the table can be used to prove that this is the first sign change. And of course you can ask, when you take higher powers like eta to some other powers, can you use, but there are not so many results in sign changes, is a particular when is the first sign change. I mean, they're all like an approximation. There's no definite formula, but actually this first sign change, non-sign change number gives you an indication when something happens with the roots. So it's like an indicator that the first irregularity with the roots are happening, or that some two roots, that an even number of roots appear. So I think this is also quite interesting topic. And when you want to go deeper in this, so there's work, of course, of Knopp, Kohn, Pripitin, and a lot of people. And we wrote a survey paper in the just appeared proceedings with Ramakrishnan, Ramki Ramakrishnan, and Sahu. This was a proceedings to the birthday of Manicam, which just appeared. When you want to go deeper in this topic, which is, I think, quite interesting to go for first non-sign changes of at least eta powers. Okay, just also to give you another flavor, there are several papers of Kostant on classification, representation of simple complex Lie algebra, and he found this formula when involving Coxeter numbers, and finally from his formula you get a non-vanishing result, which you see already here, which is more or less saying you're in the square case. And there's this also interesting topic, the Nekrasov-Okounkov hook length formula, which you run over all partitions where this is the size, you take this multiset, and they found this beautiful formula. And you see also in this formula, the hook lengths are never larger than, so the h is never larger than n. So that means, since we know this has all real coefficients, because you can connect it to the Darkey polynomials, you can also see the root zone is when you have real roots, which have to be equal to some hook lengths. Somehow is also, you have also the square case, but now you can, in the Kostant case, you have these special dimensions. Now this is more general. So for all real numbers, which are larger than when the set is larger than n square, then you have a non-vanishing. And when you write this as this Nekrasov-Okounkov polynomial, you see here the vanishing can only appear when this gives you negative, when this is -1. Now, when you go back to our result, we proved actually the linear version, and we proved it works for all complex numbers. And our proof was related to a really, I would say, lucky, sophisticated analytic proof using just the recursion formula. So it's just using the recursion formula. So that's one advantage of the recursion formula. I mean, recursion formula has some disadvantages, of course, because you have a recursion, but that was a big advantage for proving such an estimate. And there are also, this formula here was reproved independently by Westbury by using some universal characters, and Han by using McDonald's formulas. Yeah. Okay, this is Han, just what I just said. I refer here to there's in the internet still since I think 10, 11 years, a collection of conjectures of Teddy Amdepahan. Then Keyes proved together with us, he was earlier, but in a different version, one conjectures of there, and there's a recent paper of Walsh and Warner, a birthday paper to Gattenthaler, appeared last year. We wrote and had been several papers related to these polynomials, and we conjectured, and you have seen already in the definition that actually the Okounkov polynomial, Nekrasov-Okounkov, is actually a shift of our original polynomial related to the sigma function. So what we conjectured that, and have a lot of numerical evidence that this is log concave, but actually we think when you take the shift away, and that's the first case when the coefficients are all positive, and we think actually without a plus it should be already log concave. And maybe, which we don't know, it would be interesting maybe to ask, okay, let's put here any A positive. Can you prove that at least for a certain A, these things are log concave? We did not find any result. In general, maybe there's a general result saying when you have a polynomial positive coefficients and you shift it to a certain way, then it becomes log concave. It would be very interesting to know, to get, let's say, some kind of a bound and what to expect. And actually recently, under the guidance of Ken, Hong and Zhang proved some results to this conjecture. In some sense, it proved at one end of the polynomial it's log concave, and on the other side, at least it's unimodal. And he came up with another conjecture, which seems to be at the moment very interesting, but not reachable maybe at the moment. So what I want to say, there's a lot of activities in this direction. But you all know, for example, when yeah, that's what I want to say. So it would be interesting, what is open to prove the log concave conjecture? Of course, to prove anything, any result, correspondence because Pn and Qn, to put maybe to start, like how can you attack this by a theory to prove correspondence results, which results can be transferred, which are not, can you find counterexamples, things like that. Then what I said with Volterra, which is called like in the recursion case, it's like a Poincaré-Perron type. But there always you have a finite type recursion. We have, the recursion terms grow with n, which is not really well developed in the literature. Of course, extend the Heim-Laguerre Neuhauser result by using algebraic number theory and the Hurwitz polynomials. Okay, now I come to the last chapter. Bessenrodt-Ono came up in 2016, I would say, with a very surprising small paper. It looked very innocent, but they proved that some multiplicative property on the left side and some additive thing on the right side for partition numbers. And they came up with finite of course, with when A and B have to be larger than 1, because otherwise here you just multiply with 1 and you add by 1. And then with finally many exceptions. And they came up with an analytic proof by some Lehmer type thing. Of course, there's Rademacher, but there had been also some Lehmer type first, second term estimations with the circle method. And then Alanzi, Gagola, and Monaki, who is here today, they came up, I don't know if it really was expected, it's possible. They came up with a very nice combinatorical proof. And just after, and there had been several papers of back and with Bessenrodt, different type of using partition, not just partition number, other types like K regular partitions. And it turned out that this Bessenrodt-Ono inequality really has some deep structure, which a lot of other partitions have. Dorsey, Masri, and then Hu, Jagadisan, sorry for misspelling maybe the name. And then actually we just done this, some kind of a, how to say, like a training for us to go into this. We said, okay, what's happening when we try to find out on the right side when A and B grows, somehow can we go a little bit deeper in this with the exceptions when we move the M here. And then Chern-Fu-Tang came up, I think really deep conjecture after they proved the following. They said, okay, let's take not just the eta to the power of -1, take it to the minus k. So these are the so-called k-colored partitions. That means every partition has k colors. And then they proved the same inequality. And surprised, maybe not just surprising, but only in the case equal to 2 and 3, there are some exceptions. Otherwise, it's completely true. And they came also up with a combinatorical proof. And we said, yeah, but why not just why just taking the power of k? Why not taking what we've done before, integer powers or even complex powers? Is it possible to have such equation when we now plug in the polynomials before? So we saw it as a polynomization. Now you can also say, okay, this is a discrete case and that's the polynomial case. So we found the following thing: when A and B are larger than 2 and X is larger than 2, then actually for these Stargate polynomials, but we have to say now we look at the right side of the coordinate system. That means we look at positive real numbers. I mean, otherwise, of course, when you plug in we cannot have. We need real numbers to compare them, So the idea is, you can also ask why we are doing this, but we are interested in the roots. Yeah, of course, but it's the same polynomial. Maybe when you get properties on the non-vanishing side, maybe someone has an idea to say what this, because the polynomial is uniquely determined. What can you say on a much more somehow complicated side? So that's the idea why we went into this topic also.
Does this also hold if you look at it coefficient-wise in absolute value for the polynomials as polynomials in X?
Again, please.
If you compare coefficients one by one on the left-hand side and the right-hand side as coefficients of the polynomials in X, and look at them, I know that they alternate, but if you look at them in absolute value, is it also true that the coefficients on the left are larger than the coefficients on the right?
Oh. We have, I don't know, we have not thought about it.
Okay.
It could be difficult, it could be easy. I cannot say it. Maybe one should do some examples. Interesting question.
Thanks.
Very interesting question. So, at the end of the paper, Chern-Fu and Tang came up with an interesting, when you go into this topic, with a very interesting conjecture. They said when we Okay, let's see the following. It was known at that time, just before Pak and De Salvo, they proved that when n is larger than 25, the partition numbers are log concave. I mean, a lot of people, I think, miss that this was already proven 20, 30 years before by a French mathematician, but they proved much more in their paper, so it's way worse, and they kicked also this topic. And then they said, yeah, but when we go to k color, not k is equal to 1, maybe when there's a property in this direction. So this is actually, when you look at carefully with the A and B, it's like, here it's definitely like this is maybe, you know, larger than one part and the other part is smaller than the other part. So it's really quite subtle conjecture when you go it for numerically. And I was not sure if this can be proven so quickly. And actually so what we done in a quite natural way, we just polynomized it. We said, okay, we can write this as an inequation of polynomials. And because our proof actually was completely different from the proof combinatorial or the proof before. What we done is we looked at one special value of the polynomial for A and B or A varying, and then we proved that the derivative of the polynomials when you go to the right side is always positive. It's like saying we look at one line and then we prove the derivatives are positive, so they can never have a zero. That means the inequation has to be the same as going to infinity, and at infinity, of course, we are on the right side. We look at the dominating coefficient, and then we can see in the previous case that this is true. That was actually our proof. So we looked actually at k is equal to 2. That means x is equal to 2, and then we looked at derivatives, and then we had some quite, even I would say, some weird, but it worked inductive proof. And the hope was, of course, to use that technique with derivatives to take this conjecture. And we actually could prove it for b is equal to 1 for all other a's. But it was clear it's much more complicated when b gets more general. And just recently, Brinkman, Kane, Rowland, and Tripp distributed in archive, and I also got one preprint from them. Actually, they proved the conjecture. Actually, what they done is they used also a very nice paper of Iskander, Chain, and Talvor, who actually proved somehow the Rademacher formula for k-colored partitions, and but more general. Actually, I think it was not just k-colored; it was also for x. And now, Brinkman and Kane and Rowland, they made it more precise. But maybe also after that, Rowland can say, or I don't know if Tripp is around, can say something. And actually, they proved this formula. They said, okay, when this is the, that was the difference of these up and down parts of the conjecture, this one here. And then you got this asymptotic formula. This is saying for in a certain domain, this dominates this one, which they put here. And with this formula, they had been able to actually to prove the following: when b is larger than this constant, then the Chern-Fu-Tang conjecture is true. Now when you you have to plug in for each x a k. So k is equal to 2, 3, and so on. And then they had been able in a very delicate manner to prove this by also using computers, because you have an upper bound. So you have to, when you take k is equal to 2, you have to prove finally many cases. A lot, but finally many. And there's also a result of Hogarth saying when you have the convolution of two log concave sequences, then it's again log concave. And with this property and putting everything together, they had been able to use also adapted computer algorithm and changing things. And just want to say for the case, I think case equal to 5, they needed 77 days to do the final calculations, but they had been able to use the case K2, 3, and 2, 3, and 2, 3, 4, and 5, I think, to get with this convolution technique all the others. And of course, for every x, they have proven that our conjecture is true when you just have to take b is larger or equal than this. But of course, when x gets large, it's almost not possible to prove this in many cases, and you cannot use the convolution techniques because you have to go very close to x is equal to 2. So whenever you choose one x, there's a smaller x. So the continuous case is still in the general case open. And now just to end my talk, so what and it's just recently published research and number theory. We got now we have for 1, 2, 3. We have proven it. We also find out when b is odd, then actually you can even start with x equal to 1, because this is possible, and in the even case you really have to start by 2. So this is proven, and our proof method, as I said, works by fixing one point and looking at all these a's. So fixing a b and a point and looking at all a's, and then looking at it and proving that the derivative is larger or equal to 0. But it's much more complicated than in the Chern-Fu-Tang conjecture. And now just to give you impression why we believe that maybe the continuous case has also advantages, because of the following. When you fix b is equal to 27 or b equal to 28, and you vary the a, here is the a varied and here the a, and you consider this as a polynomial, we calculated the roots of the polynomial. The red ones are the complex, and the blue are the red. And since we know by comparing the leading coefficients, here the coefficient, the polynomial has to be positive. That means when this is the last root here and here, from here on, the delta is always positive. Now this picture tells you, okay, you have some exceptions, which you know from Ono, from Bessenrodt-Ono, but when you go a little bit higher, you see the exceptions, you are left. So that means it's all, there's no root actually. Essentially, there's no root on larger than 1 here. That means actually the constant which is suggested by this very deep and hard circle method proof of Brinkmann et al. Actually, it turns out at the end the constant it's actually very low. But so their method suggests that the constant gets larger and larger, but because of the technical proof by using the circle method. But actually, it seems to be numerically, when you look at the roots, that these delta polynomials actually when x is larger than 1 or 2, actually are always positive. So maybe one should look in this direction to prove it. And we outlined in our paper a way to prove it with certain steps. Okay, I end my talk with 7 challenges, which maybe in the future can be proved or looked at it. As I said before, it's maybe worth to vary the g and the h to get properties of these polynomials, to prove the Hurwitz property, which will open actually to look at these polynomials really as characteristic polynomials of dynamic systems. So we would have completely new techniques to study these polynomials. Okounkov conjecture. to find a root distribution, one can also say, okay, we cannot do it individually, but what's about n goes to infinity? How are the roots behaving? I mean, this has been done for Laguerre, for all orthogonal polynomials, by semicircle, by beta distributions. And actually there's some work in progress at the moment in this direction. Now, as I said in the beginning of the talk, when you look, you converse it, at the moment, there is no negative integer known, no negative integers known, where for all n, this is not 0. So I just converse the Lehmer conjecture and the lacunary. Of course, when you have minus 24, this would mean the Ramanujan conjecture, but it's not known that for any other integer that there's no 0 for these polynomials. And of course, as I just said, it would be also we would suggest Marcus and I that these to look at the polynomization of this. And finally, it would be maybe interesting. We worked a little bit, but it would be really interesting to look at these polynomials here and to ask yourself: is there any kind of hook length formula when G is different from sigma and identity here? And finally, I want to say that the plots we had been very much supported by our colleague and friend Robert Tröger, who also was involved in the polynomization of the Chern-Fu-Tang conjecture. Okay, that's the end of my talk. Thank you very much for your patience.
All right. Well, thank you, Bernhard, for a very nice talk. Any questions? Oh, sorry. Did someone have it? Yeah, Augustine.
Yeah, it's an interesting talk, and the Bessenrodt-Ono theorem, which we proved by combinatorial means. Well, as far as I'm concerned, the challenge for a purely combinatorial proof still exists, and I wish it were included in your challenges, because what we did there is a bunch of injective maps and cutting and pasting stuff. So it's not really, it doesn't give you that pleasing feeling of a neat, smooth combinatorial proof. And now the extent to which it has gone, as I told you earlier in an email, it has gone quite far, to the extent that when I look for this, my good old combinatorial thing, I don't see it much anymore. You're taking it beyond recognition, you know. But it's a great talk, and this is not my last time of looking at it, and you have opened some nice way to really extend the thinking about it. So thank you very much.
Thank you. I mean, this conjecture is now proven, which I really I did not thought that it goes so fast. By Brinkmann, Roll, and Al, but of course still there's a combinatorical. At the moment it's a high machine of using asymptotics and computer calculations, and I was really impressed. They maybe Roland can say, Larry can say something, but they used, I think one calculation was 77 days.
Yeah, and we were, but that's a great question, Augustine. Of course, it would be great to have combinatorial explanations as well. Absolutely. We had to be very careful both with the asymptotic estimates well, it's a lot easier with the circle method to get asymptotic formulas, but to get exact formulas with explicit error bounds, we had to be very careful both to make those error bounds as sharp as we can to limit the number of computer cases. And the coding required a lot of subtlety in how it was coded as well. And that's really Ben Kane is very good at that that kind of computational stuff. But yeah, that was quite a difficult calculation. It was difficult to set it up so that it would run enough cases quickly enough. Yeah. For a while, I didn't think we would actually be able to prove every case, but it's much nicer to say, you know, well, if you can only prove it in all but finitely many cases, then that's easy to do. And if you can prove it in all but like 100,000 cases, it's like, doesn't feel like much better. But if you can prove it in every single one, then you can just state, I you know, prove the conjecture. So it's, yeah, somehow worth the effort, but only if you really get there.
Mm.
But it's much easier, of course, if you're not worried about being very precise with the analytic estimates. It's much easier to just say it's true for all but finitely many. That kind of thing is much easier. But yeah. Any other questions for the speaker? I have a question. I was just wondering if you could say a little bit more about the philosophy of Rota. I mean, you mentioned the overall philosophy. I just was wondering, like, specifically, what else do you expect to like get from the philosophy, or what? I've seen some things in of Rota's work mentioned before, but if you could say a little bit more about that.
I mean, of course, he is also famous for this, I think, umbrella calculus, which he wrote some books and which was not clear at that time to make it on a solid basis, but he and his colleagues done that. I mean, what he said is, you know, now the Lehmer conjecture can be formulated as saying the minus 24 is not a root of these polynomials. So, which is, so what he said is, and of course, when you look at the product formula in the beginning, it can be also seen as a pure combinatorical question. Can the product ever, when you look at the coefficients, then can this ever be 0 of this 1 minus q to the n to the power of 24 product? So you start with a combinatorical question, and he said, and I was very surprised some years, 2-3 years ago when I saw that, and which fits completely in our philosophy, that he said it should be possible, and or he wants to see that in the future, that that combinatorial problems can be translated in that. And of course, you know, so one idea is, and we have not got a result yet in this direction, we would like to prove, for example, that the roots get infinitely many close to minus 24, for example. Or maybe there are some holes in the whole plane, like maybe by some integer, very large one, where there's a hole, that means the roots are not getting close. Or we can prove that's the opposite, that it's dense. So that would be actually a result completely in this philosophy by using really this analytic approach. And I mean, one main thing which I still hope which makes the game is that these polynomials have finitely many roots. So we got some finite property, but you know, there's this paper of Serre in 1985 where he proved this Laguerre property. Mm-hmm. And he wrote down the first 10 polynomials, actually quoted them from Newman. Mm-hmm. So they went to 10, they even did not write down, maybe in the 10th case, there are complex roots, because in the Abba-Dehaan's conjecture, he conjectured still the roots are real, which we disproved by looking at 10. And up to 4, they're only integers. So, and yeah, and actually, which I did not mention, actually, the proof of Serre, that's so-called lemma 3, is reduced to mod 11. That means he needed the first 10 polynomials, which he reduced the whole problem of CM forms to that. Yeah, it's like, maybe we want to encourage also some people from combinatorics to join.
Yeah, absolutely.
But what Key said, actually, it's interesting. Maybe, I mean, that's also something with looking at the coefficients. but it's a little bit what you said. It only gives the work only, gives success when you prove it at the end. Otherwise, you prove some formula, but you're not getting to the end. So it depends a little bit on your intuition. When you see something, of course, it would be great. If not, you may just get lost for 1-2 years.
Yeah. Okay. Yeah, Jeff's here. I know Jeff knows about this Rota stuff as well. And you said you actually took a course from him, right? Where he explained, where he talked a lot about this philosophy.
Well, I'm not sure of that. I did take a course where he was talking about the umbral calculus, but I was too young to get as much out of it as I could have.
Yeah, it's fascinating stuff, but I've never understood what the umbral calculus really does and what it's. Didn't you say
Eric Temple Bell did a lot of stuff in the umbral calculus? And
yeah, you were telling me
colloquium.
He wrote Eric Temple Bell. He wrote a book or something, or
the Colloquium Lectures of the American Math Society.
Okay,
it's in the Colloquium series.
Mm-hmm.
As I understand it, it's very hard reading.
Yeah,
I mean, there's something also with, I think, with Rotman together.
Who?
Rottman, I think they wrote also some long article on this. But what I done is actually my connection was this quote he put. This was put in several places in the internet. Also, he gave an interview on his philosophy on concrete proving things in mathematics, and not doing this Adele, whatever. So I have never met him personally, but that's what I read, and I was, yeah. I think it's a good motto for the whole thing.
Maybe you were referring to Stephen Roman.
Oh, Roman. Sorry, yeah, Roman. Yeah.
He wrote a book and he wrote a paper, maybe in advances on the umbral calculus, and then Roman wrote a book.
Okay,
yeah. He was a student of Rota, I think.
Mm.
All right. Other questions for the speaker?
I just have a comment about this question about coefficients, and it's actually not true. So they have, I mean, if you take the difference, they have positive and negative signs. So I quickly checked it. Right. So we don't have it for this. And I think if it would have been true, the proofs would be much easier if we would have a clear, bias from the coefficients.
Thank you, Marcus. Now I remember. Actually, the smaller powers. I mean, when you start from the right side, power of x to 1, there you see you get negative coefficients. Yeah, actually, that was one trial we done, and then we hoped that it's only we see some pattern, but it did not work out.
Yes.
But of course, maybe there's some way to see some dominant coefficients, and yeah. So thank you. I forgot that approach.
All right. Well, let's thank the speaker again for a very lovely and varied talk with many different interesting topics and suggestions for future things to look in. It's really a broad thing with a lot of different facets to explore still. Yeah.